This picture is the impression of childhood, probably of every person on this planet, everyone, throughout the history of mankind. The sun was worshipped, considered a god. The sun created everything and everyone within the solar system, the leaf, the tree, you and me, the earth itself, and all the planets. But our star is not only the creator, but also the destroyer, a huge thermonuclear machine 1,000,000 times the size of the earth. The power of billions of hydrogen bombs radiates from the sun every second. Nevertheless, everything we see on Earth was created in the solar forge. But how did the sun itself come into being? How does it work? How did the planets of the solar system arise? How did the sun die, if at all? It's time to get to the bottom of it all. Learn about the origin of sunspots, about the quantum tunnel effect. Find out why our star exists in a constant state of struggle. And a struggle with whom? We're setting up an expedition, urgently preparing for a space voyage. Our voyage is not a fairy tale or a fantasy, but a kind of thought experiment based on objective scientific data. We will see the history of the most important star for us from the beginning to the end. So, to the source of life, the sun. Our first stop is not in space, but in time, the known universe. We are here for a short time. And what was the universe back then? Hydrogen, and practically only hydrogen. What you see are giant nets of hydrogen. They're billions of times the size of galaxies. Hydrogen is what started the formation of galaxies, and one of them is ours. People would call it the Milky Way. Now, let's go 10 billion years into the future. Our galaxy is already mature, and there are billions of stars in it. The sun wasn't the first. That's the kind of beauty that is the cradle of our sun, literally. In science, it's called a stellar cradle. A stellar cradle is a type of interstellar cloud, also called a molecular cloud. In such clouds, there are regions of increased density in which stars can form. In general, to make a star, you have to. Here's the recipe. You have to take very, very many hydrogen atoms, mix them up, and squeeze the whole thing very hard. Okay, there's enough gas in the molecular clouds. But where does the pressure come from, and how do we compress it? And the thing is that this, at first glance, harmless invisible gas hydrogen is really harmless, as long as there is not much of it. But the cosmic scale does its job, and gravity provides it all. The enormous size of such clouds amass millions of times larger than any, even the heaviest, star makes gravity compress the hydrogen atoms with incredible force. We can say that there is a law of the universe. If there is too much of something, the law of universal gravitation is bound to compress it all to the limit. Thanks to this law, galaxies appeared after the Big Bang, and stars appeared in galaxies. And here we notice another characteristic feature of how our universe works: rotation. In an attempt to find a common center of mass, this whole structure began to rotate around itself as if it were a funnel of water. The rotation accelerated, as did the pressure and temperature inside the cloud. The gas became plasma, the fourth aggregate state of matter, even hotter. Most of the mass gathered in the center, and the rest flattened into a disk. True, unlike water in the shell, all this happened very slowly, tens of millions of years. Why, by the way, into a disk? Again, because of gravity. When there is a well-defined center of mass, all objects that revolve around it tend to do so closer to a two-dimensional plane. It's easier for them that way, the law of least resistance. That's why the disks around Saturn, the accretion disk around black holes, and most galaxies are flat. But back to the sun. It's still forming. But we can't yet consider the sun to be a star. Right now it's a prototype. What distinguishes a prototype from a true mature star? Protostars are doomed to destruction. Their existence is a small, on a cosmic scale, of course. Yes, protostars owe their existence to gravity. But if nothing changes, it will destroy them. But look what happens now at the center. The enormous pressure and extreme temperature in the core of our prototype eventually triggered a thermonuclear reaction. This is what allows the sun to live on. The start of nuclear fusion in the core is a triumphant transition, you might say, from the stellar embryo to the sun as we know it today. But look what happens now at the center. The enormous pressure and extreme temperature in the core of our prototype eventually triggered a thermonuclear reaction. This is what allows the sun to live on. The start of nuclear fusion in the core is a triumphant transition, you might say, from the stellar embryo to the sun as we know it today. Do you know where carbon and oxygen came from on Earth and in the universe in general? The elements didn't just appear by themselves out of the ground. Carbon and oxygen are types of atoms. Stellar synthesis of the elements is the only process by which hydrogen atoms are transformed into the other elements of the Mendeleev periodic system almost one by one. That's where carbon and oxygen and everything else comes from, stellar fusion of elements. And such fusion requires pressure and the highest temperature, which is what is found in the center of stars. So the sun is the great cosmic forge. And one more point. Let me remind you that it is fusion that allows the sun to exist. The fact is that the very gravity that created the sun can also destroy it, compress it to a state that will inevitably lead to an explosion. The life of the sun can be thought of as two opposing forces, gravity and radiation. Gravity is compression into the center, and radiation is expansion, radiation outward. And it is fusion that is responsible for the radiation. The process of converting hydrogen atoms into helium atoms, namely 4 hydrogen atoms into 1 helium atom, creates a huge amount of energy. Every second, the sun releases the energy equivalent of 1 trillion megaton nuclear explosions. This energy moves outward with tremendous force and fights gravity. The balance of these forces is called the sun's hydrostatic equilibrium. And this is the reason why the sun exists. As it leaves the star, solar radiation, or solar wind, travels farther into space. It is to the solar wind that we owe both heat and light of all spectra. But now, billions of years ago, the Earth does not yet exist. But there is a so-called protoplanetary disk. And unexpectedly, the forces of gravity, on the one hand, and the solar wind, on the other, are again competing. The solar wind is trying to blow dust into space, while gravity is trying to attach it all to the sun. Thanks to the opposing forces that create electrostatics, the dust particles inside the disk begin to form so-called planetesimals, celestial bodies that resemble asteroids, the building blocks of all the planets of the future solar system. Here, for example, the Earth is formed next to the Sun. Interestingly, the water on Earth was also created by the solar wind. Not immediately, not next to the Sun. Otherwise, all the water would have evaporated instantly. Once formed, the Earth flew away from the Sun, and there, at about its current orbit, it began a process called space weathering. The hydrogen ions, protons carried by the solar wind, penetrated into the dust particles of the protoplanetary disk, where they oxidized minerals, creating first hydroxide Ho, and then water Ho. Clouds of this frozen, water-rich dust fell on the young Earth, creating oceans, seas, and rivers. And 10 million years later, the solar wind would finally blow the remaining protoplanetary disk into interstellar space, stopping the growth of the planets. After 50 million years, the nuclear reactions inside the Sun will stabilize. Our Sun will officially stop being a prototype and become a yellow dwarf. The Sun will create the heliosphere you now see on the screen, which protects the entire solar system from dangerous galactic radiation. And now begins a long era, 4.5 billion years of the Sun and the solar system. For all these billions of years and to this day, the Sun has determined and continues to determine events on our planet. It controls the weather, ocean currents, seasons, and climate. The Sun is the perfect size, brightness, temperature, and distance for life on Earth. If anything were even slightly different, life as we know it would not exist. But in 2012, more recently, a solar storm could have created a real disaster. The Sun released two massive plasma clouds that were literally weeks away from colliding with the Earth's atmosphere. These plasma clouds, created by coronal mass ejections, formed the most powerful solar storm in 150 years. Physicists compare the 2012 storm to the so-called Carrington solar storm of September 1859. Then there was the strongest geomagnetic storm on Earth. Auroras were visible all over the world, including at the equator. And what was absolutely fantastic, the telegraph systems began to spark and burn, even those that were completely shut down. Well, then, in 1859, only the telegraph networks were affected. Today it would be a real catastrophe. Civilization itself as we know it today might disappear, as cell phones, credit cards, and the internet would become useless. Such outbreaks are the kind of solar weather that should be studied and predicted. It is also curious that, like terrestrial weather, solar weather is seasonal, with a cycle of 11 years. So what determines the seasonality of solar weather? Let's look at how the Sun's magnetic field behaves. The Sun's magnetic field is generated by electric currents that act like a dynamo. These currents, in turn, are generated by flows of hot ionized gases or plasma. Yes, the Sun, in addition to being a thermonuclear reactor, is also a dynamo. Flipping of the Sun's magnetic poles. During the first half of the cycle, the magnetic North Pole is in the northern hemisphere, and the magnetic South Pole is in the southern hemisphere, and then they switch. The peak of this cycle was in 2012. The magnetic cycle controls the movement of magnetic fields in the Sun, and therefore the solar weather. For example, Dark spots on the sun are places of electromagnetic field concentration, and they are so strong that they inhibit inflows of solar plasma. Because of this, the areas cool down, so we see them as black relative to the rest of the star's surface. Magnetic fields can even create tornadoes on the surface of the sun. A plasma tornado. Can you imagine that? And it can rotate at up to 260,000 kilometers per hour. On our boring Earth, air tornadoes reach negligible speed, just 500 kilometers per hour, but here 260,000 a plasma vortex. And what about solar flares and coronal mass ejections like the ones we avoided in 2012? Flares occur when the most powerful magnetic fields on the surface of the sun become too tangled. Like a rubber band that tears when it's twisted too much, the tangled magnetic fields release enormous energy when they burst. Sometimes flares release so much energy that they take part of the solar corona with them and carry it into space. And then billions of tons of incredibly hot plasma are sent out to send a fiery plasma solar greeting to, for example, Earth.
How does the sun work inside? That's of separate interest. We are already familiar with the solar corona and the photosphere.
You can get a good look at the corona during a solar eclipse. Here it is. Between the corona and the photosphere is the chromosphere. This is where the flashes and vortices occur. Beneath the chromosphere is the photosphere. The visible surface of the sun is ostensibly only 400 kilometers thick, which is very small relative to the solar dimensions. In the photosphere are visible thermal columns, zones of convection. In powerful telescopes, the tops of the columns look like accumulated pellets. Here, take a look. Each pellet has a bright center, which is a hot gas. The gas rises upward along the thermal column. The dark edges of the pellets are the cold gas. The cold gas flows back down the column convection again, like layers of boiling water. Here's a comparison. Recall that it is this convection motion that is responsible for the entire dynamo of the sun, for generating that most powerful magnetic field. Going down, there is a zone of radiant energy transfer, as it is called. Radiant energy is photons, light. In this zone, energy is transferred as a result of thermal radiation. During this process, each photon emitted in the nucleus, after traveling a short distance, is absorbed by a neighboring ion. Recall, an atom with a detached electron is released by that ion and absorbed again by another, and so sequentially, one after the other. The atoms are essentially throwing photons at each other and passing them on, like in a game of hot potato. A single photon can continue this process and move around inside the radiation zone of the sun for almost 200,000 years. Imagine, a photon appeared in the core of the sun, and then only 200,000 years later it will come to you on an early summer morning. There you go. Let's go down further. And then we have, yes, the solar core. And then we have, yes, the solar core is more than 1,000 times the size of the Earth. And it's a huge fusion furnace. Let's now look at this process, the process of thermonuclear reaction, in more detail. So, as we already know, The basis of the process is the conversion of 4 hydrogen atoms into 1 helium atom. Hydrogen is the first element of the periodic system. Hydrogen is the first element, helium is the second element. Hydrogen is a very light atom and helium is heavier. But 4 hydrogen atoms are still slightly more massive than 1 helium atom. This difference in mass is what turns into energy. And how does this differ from the release of energy in a nuclear explosion from the release of energy and chain reactions in nuclear reactors on Earth? Because the process on the Sun is reversed. Both nuclear reactors and nuclear bombs on Earth divide heavier and more unstable atoms into less heavy ones. The best known elements for these reactions are uranium and plutonium. In the solar core, on the other hand, light hydrogen produces heavier helium. So why can't we use the same reaction that takes place on the Sun? We don't need any heavy and unstable atoms that create dangerous radiation. All we need is hydrogen. And that energy is efficient because you can get more energy from a glass of seawater than you can from burning a barrel of oil. Plus no waste. The temperature in the solar core is in the range of 15 million degrees Celsius. Reactors on Earth can achieve this temperature. But there is one problem. This temperature is not enough for a thermonuclear reaction on Earth. There you go. Unexpected. That's right. Under terrestrial conditions, such a reaction requires about 200 million degrees Celsius. Yes, that's right. It takes a lot of heat to fuse 4 hydrogen atoms into 1 helium atom. All because the atoms don't want to combine at all. All because the atoms at all they repel each other with tremendous force. Do you remember from school that all protons are positively charged? And according to Coulomb's law, like-minded charged bodies repel each other. But the temperature of 200 million degrees Celsius can accelerate the atoms to the speed at which they can overcome this barrier. But why is there only 15 million degrees Celsius in the solar core? The answer: because there is the so-called quantum tunnel effect. The quantum world is a world of probabilities. Simply put, in the quantum world, any particle is a quantum cloud of positions and possible states that exist simultaneously. How's that? Here's how. To give you an example, if you are quantum, at the same time in one room you are watching TV, and in the other room you are doing housework. According to classical from the physics textbook laws, according to classical from the textbook probability that protons at 15 million degrees will attract to each other and not repel each other does not exist. But quantum physics allows for such a probability. And what is happening in the core of the Sun is the best proof that the laws of quantum physics work. Protons jump the very distance after which the repulsive force ceases to act, and a strong attraction takes effect. That's what creates helium. This doesn't happen on Earth because of the low probability of such an event. And in the solar core, the volume of which is millions of times the volume of our planet, this happens, shall we say, predictably often to maintain a stable thermonuclear reaction. You could say that the Sun is playing a lottery with a minimum chance of winning by buying a quadrillion tickets and winning. Along with the Sun, the entire Earth wins. Our planet receives 173,000 trillion watts per hour from the Sun. And that's more than all of humanity's energy consumption in a year. Yes, but unfortunately, we don't use even 1,000% of that energy. In the future, perhaps we will learn to use all the energy from the Sun that reaches our planet. And then we won't even have to build fusion reactors with the quantum tunnel effect. In the distant future, we can go even further and take a swing at all of the Sun's combined energy. Theoretically, the Dyson sphere, a huge sphere around the Sun that absorbs energy, will help to do this. To give you an example, if you are quantum, at the same time in one room you are watching TV, and in the other room you are doing housework. According to classical from the physics textbook laws, according to classical from the textbook probability that protons at 15 million degrees will attract to each other and not repel each other does not exist. But quantum physics allows for such a probability, and what is happening in the core of the sun is the best proof that the laws of quantum physics work. Protons jump the very distance after which the repulsive force ceases to act, and a strong attraction takes effect. That's what creates helium. This doesn't happen on Earth because of the low probability of such an event. And in the solar core, the volume of which is millions of times the volume of our planet, this happens, shall we say, predictably often to maintain a stable thermonuclear reaction. You could say that the sun is playing a lottery with a minimum chance of winning by buying a quadrillion tickets and winning. Along with the sun, the entire Earth wins. Our planet receives 173,000 trillion watts per hour from the sun. And that's more than all of humanity's energy consumption in a year. Yes, but unfortunately, we don't use even 1,000% of that energy. In the future, perhaps we will learn to use all the energy from the sun that reaches our planet. And then we won't even have to build fusion reactors with the quantum tunnel effect. In the distant future, we can go even further and take a swing at all of the sun's combined energy. Theoretically, the Dyson sphere, a huge sphere around the sun that absorbs energy, will help to do this. Here's a look at what that might look like. We may have to saw Mercury apart to build a Dyson sphere. Humanity would then be an interstellar civilization. And would it even be called humanity? Question. For the sun, 1,000,000 years is like a couple of days for human life. For the sun, the entire history of humanity is literally a moment. The whole history of mankind, but our star is not eternal either. As we remember, the sun was a prototype for the first 50 million years and then became a yellow dwarf. In fact, to the human eye from space, the sun emits a completely white color. It only appears yellow because of the Earth's atmosphere. A yellow dwarf is a scientific designation. Even more scientific, the sun is a main sequence and G-spectral star. In essence, these parameters are set at the very beginning of the star's birth, namely the mass, that part of the molecular cloud from which the star is formed. The sun is not eternal because there is Einstein's most famous formula equating mass and energy. According to this formula, energy equals mass times the speed of light squared. What the sun is doing with the quantum thermonuclear reaction is burning up its mass and thus converting mass into energy. Yes, in our universe, mass is always equal to energy. That much of the total mass of the solar system is taken up by the sun itself. Even the giant Jupiter is no match. Not even the giant Jupiter is no match for our Earth. All the planets in the solar system altogether, plus the asteroids, comets, satellites, and moons are all 0.14% of the solar mass. The sun weighs as much as 330,060 Earths, and every second 600 million tons of hydrogen is converted into 596 million tons of helium in the solar core. Where does 4 million tons of mass go? According to Einstein's formula, they are converted into energy. That is, in the form of energy, the sun loses every second, and how much energy is enough? The sun is now in the middle of its life, the age of our star. Paradoxically, as the sun loses mass, it grows. Yes, over time, the sun is getting brighter and bigger. Today, the sun is about 14% bigger than it was at birth. This is due to a redistribution of substances in the core. There's less hydrogen and more helium. The core thickens, gets hotter and heavier, because helium is heavier than hydrogen. The temperature goes up, fusion starts going even faster, and it's happening right now. You get up in the morning, you have breakfast, and it's happening, but extremely slowly. The sun's brightness is currently increasing by about 1% every 100 million years. That doesn't sound so scary. But if we start traveling through time again and move, say, 600 million years ahead, then the brightness of the sun becomes critical for life on Earth. Photosynthesis will become impossible. The extinction of plants will kill almost all animals, because plants are the basis of the food chain. And in about 1 billion years, the solar luminosity will be 10% higher than at present. The atmosphere on Earth will become a humid greenhouse, and this will vaporize all of Earth's oceans. Imagine sunsets and sunrises in this unsightly future. And where is that harmless, cheerful morning sun that shines through your window? You look at it and squint, but it turns out that in 1 billion years it will burn all the water on Earth. And believe me, that's just the beginning. The next stage is the red giant. It sounds scary, but the reality is even scarier. When the hydrogen in the core of the sun runs out, and almost all of it consists of helium, the hydrostatic balance will be broken, the reaction in the core will stop, and the gravitational force compressing the sun will take its toll, and the core will begin this collapse. The familiar radiant energy emission zone will begin to collapse along with the nucleus and heat up. So what will happen? There's still enough hydrogen in the radiant zone, and then this hydrogen will accumulate around the nucleus, and a layer will emerge where the classic thermonuclear reaction will begin again. Yes, the radiation from this new layer will keep the sun from collapsing. But the helium core will continue to shrink and thicken, and eventually this will lead to an uncontrolled expansion of the outer layers due to pressure. Again, the paradox. As the core shrinks, the sun itself will begin to grow very rapidly, as if it were a cocked hose with a high pressure of water. What's next? Next is more, literally more. The star will reach 300 million kilometers in diameter, absorbing Mercury, Venus, and come close to our Earth. Here, look, such sunsets are waiting for us in 2.5 billion years. The sun is halfway up in the sky. It's beautiful. Oh, and don't forget about the dense helium core. It's still heating up, and at some point, the temperature inside will trigger a new fusion, already helium-based, turning helium into carbon and oxygen. This will reduce the pressure on the outer layers. The sun will become smaller again. So what? Is the Earth saved? No. The process will repeat itself. Then, when the inert dense part of carbon and oxygen atoms appears inside the nucleus, this will happen quickly. And in 100 million years, the sun will be huge again. This time it will cross the orbit of the Earth. The sun will be about 10 billion years old at that point. The sun will celebrate its jubilee in a big way and literally swallow the Earth at the second attempt. But this does not mean that the Earth will disappear right away. It will still suffer. The outer layers of the sun will not be very hot. And for millions of years the Earth will rotate inside the sun and gradually melt, becoming smaller and smaller and smaller until it disappears in the plasma fire that spawned it. What's next? Because of the expansion, the sun will begin to lose its outer layers. They will form a beautiful nebula. Gradually, only the multi-layered core will be left of the sun, so the sun is 12 billion years old. After all the helium has turned into carbon, the sun will become a white dwarf about the size of the Earth. The sun is now too small to start atomic reactions. Not enough gravitational force to start turning carbon into iron, for example. So the nuclear furnace will stop. This time forever, the gravity of passing stars will drag the remaining planets away. And the solar system will cease to exist. The residual electromagnetic energy will be radiated for a very long time. The white dwarf will last for trillions of years. What happens next depends on the fate of the universe itself. If it continues to expand, the sun will be safe. It could go on like this for quadrillion years, and when our white dwarf runs out of energy, it will turn into a black dwarf, which means that the sun will finally go out. Eventually, the cooled carbon will form into a single giant diamond crystal. Yes, this final point, the diamond ball, the diamond, is a gift from all of us to the universe. The universe will be very different then, though. Maybe it won't like this gift of ours. There will be black holes flying around in empty space. There will be no more galaxies. Most stars, if not cooled down, will fly away from each other at distances billions of times greater than the entire radius of the universe known to us in our time. The universe will be dark, not as dark as our diamond, for sure. And in this dark void of unknown destination, and in this dark void will fly the diamond ball that was our sun an eternity ago. It won't go out anytime soon. As long as it's alive, we're alive. In this beautiful world painted by the sun, we are lucky. If you gaze long into the purple-orange disk, it seems as if you are flying toward it, right toward the sun.